waves in a spherically layered medium. But before I do that, there might be a few things that you might like to know. We did layered medium and almost a lot of things that you need to know about layered medium, but there might be something that you might want to know, an isotropic layered medium. And this kind of layered medium is when each layer is described by a permittivity tensor and a permeability tensor. And this might be something very difficult to solve. And there are no closed form solution for this kind of problem. But you can still solve this problem when you have plane waves propagating through this layered medium. The essential physics that I'd like you to know is that when we have isotropic layered medium, we have TE and TM waves. And the TE and TM waves propagate with the same phase velocity and the same k vector. But if you have an anisotropy, such as this one, the TE and TM waves are split in two kinds of waves called type 1 and type 2 waves. For lack of a better name, we call them type 1 wave, and then type 2 wave. And they will have different angles, different k vectors as they propagate through this layered medium. And you can still match boundary condition and solve out this problem. Okay? And this kind of problem could be useful in geology, say if you work for Schlumberger. And they are doing the prospection of the underground earth. Like they might look for oil, and they might have an oil rig, and they put sensors, and then they want to look for what is underneath the earth. The earth is made from sedimentation. Sedimentation is the deposit of materials in the earth over a millennium, millions of years, and then you have a lot of layered medium. They are actually not horizontal like what we study in the textbook. They usually kind of curve. But you can understand a lot of essential physics by studying this simpler problem of the wave through layered medium. So there's one thing, and you might encounter this in other kinds of materials, like metamaterials or some of the things like graphene nanoribbon and graphene nanolayers and so on. You might have to model some of this with an isotropic permittivity tensor and so on. But we will not talk about the detail of how to do that. If you need to learn how to do that, you can read that from the textbook. Okay? Today I'd like to talk about spherically layered medium. That is, if you have a sphere that is layered as such, how do we solve for the solution of such a problem? Okay? And in order to solve this problem, it turns out that very strangely, you can, if this is R direction, okay, you can divide the wave into Tm to R and Te to R. You can actually decompose the wave into Te and Tm type as well for isotropic layered medium. In isotropy, again, you have this kind of complication. But for isotropic layer medium, this decomposition is possible. Okay? Very strangely, this is possible in a spherically layered medium. If you go to a cylindrically layered medium, which I will not talk about in this course, but written up in the textbook, is that the Te to rho, or you can use either way to decompose this problem. Te to Z and Tm to Z are always coupled. Most of the time they're coupled. Occasionally they are not coupled, and like the case of optical fiber, the Tm0 modes and Te0 modes are not coupled, like 0M T0M in the optical fibers are not coupled, but most of the time they are coupled, TE and TM, and in optical fiber we call them the HE mode or the EH mode, indicating that in this case you would use TE to Z, this would be HZ to model this, you would use EZ to model this. TE to Z means you can model it with HZ, TM to Z means you can model it with EZ. But then if they're always coupled, you call them EH or HE modes in optical fiber. And this is also true for cylindrically layered medium. And the textbook gives you the detail of how to solve the problems when these things are cylindrically layered. But we'll not talk about them in detail. You can read them, but I'll talk about this problem, which could be quite interesting. Okay? This problem was first solved, I guess, by Debye. Debye was a student of Sommerfeld. He also won the Nobel Prize. I don't remember, but he made a lot of contributions, not only to physics, but also to chemistry and so on. I don't recall what he got the Nobel Prize in. But in order to characterize the TM waves, you define them with the H field of this fashion. Okay, and then in order to characterize a TE wave, you define them with a potential of this kind, and pi E and pi H are called the bipotential. Okay, and you can clearly see that there's no R component in this field. You can clearly see that there's no R component in this field. So this must be a TM to R wave. This must be a TE to R wave. And R in this case is called the piloting vector, the pilot vector. Because it's a vector that causes the field to be transverse to R. It causes the field to be transverse to R. We call it the pilot vector. And I'd like to prove to you that this is a possibility for a solution to Maxwell's equation. In fact, for a homogeneous medium, you can discuss the case of a homogeneous medium first. This must be true, that curl cross HTM minus k squared HTM must be equal to 0. And that curl cross ETE minus k squared ETE must be equal to 0. This must be true. Right? This has to be true. Why is this true? Because these two equations. Why should this be true? Can anybody give a good reason? It's actually a very simple reason. I just want to make sure that you're awake and not sleeping. Right? So why is this true? Aditya, why is this true?
That's a source-free wave equation.
Source-free vector wave equation. You can derive this from the source-free Maxwell's equations. Homogeneous medium is very important. If the medium is not homogeneous, you will have maybe an epsilon stuck in here and a mu stuck in between here. Okay, for inhomogeneous medium. For homogeneous medium, this is true. So we have to prove that this Debye potential, when expressing and when piloting the field to be of this form, satisfies this equation. Okay, so there are some algebra to do here. By the way, Debye in this book about 1909, quite a long while ago, before the Sommerfeld or Weyl identity, in fact. Okay, so say if you plug it in here, then we want to figure out the fact that the H field, okay, that let me see what we want to show. We want to simplify this curl of R pi, and this pi can be pi E or pi M. we want to see if we can simplify this first. And if I were to look at this, then I would first look at this term. Okay, look at this term first. Curl cross R prime. Okay, and I think most of us know how to simplify this from our undergraduate knowledge. That is equal to gradient of the divergence of R prime minus the Laplacian of R prime. Okay, this must be curl of R prime. Okay, everybody agrees? You remember this knowledge? Okay, everybody knows that. And then if you plug this into the above again, you take the curl of this, the first term goes away. Okay, what you have then is that you have curl of Laplacian of R prime becomes the first term. And then the second term becomes what? Minus k squared curl of R prime. Okay, and we want to know that if this in fact satisfies this equation, if it does satisfy that equation, then this has to be 0. Is this truly 0? Okay? And I want you to think this thing slightly differently. That let me see. Okay, I want you to think that the Laplacian of R prime, okay, this is slightly tricky. You can think of it as consisting of 3 terms. In Cartesian coordinates, then I can exchange the order. I cannot take this outside because R and Laplacian do not commute. However, if I write them in terms of x, y, z coordinates, then I can write this as this. The x hat is a constant, I can take it outside, and then I can have y hat Laplacian y pi plus z hat Laplacian z pi. Okay? In other words, if I write R as being x hat x plus y hat y plus z hat z, when I substitute that in, I can exchange the x hat, y hat, z hat, and obtain the expression over there. Okay? And then if I look at this now, Laplacian of x pi will consist of 3 terms. Okay, there will be the transverse to x. Let me just denote that by s squared x pi plus partial x squared x pi. Okay, but because these are partial y and partial z, this means partial y and partial z. Okay, I can exchange my x and put it outside. So this is the same as that one. Okay, but this one I have to use the chain rule. I use the chain rule and use the fact that f double prime f times g double derivative is f double derivative g plus 2 f single derivative g single derivative plus f g double derivative. You know this rule, right? Everybody knows this rule. If you differentiate the product of 2 functions 2 times using the chain rule, you get that. So I'm going to use the chain rule to simplify this. So the double derivative of one of them is 0, and then I will have 2 single derivative. Single derivative of this is equal to that, partial x pi, and then the double derivative of the last term. So this is going to simplify to that. Okay, I repeat this for this term, that term, and that term, and you know what I get now. Okay, I repeat for all the 3 terms, then this becomes R, I can collect this together, and this actually becomes 2 partial x pi plus x Laplacian of pi. Okay, so this together with that gives me that thing, and then I will have 2. And if I collect all the 3 terms together, this will give me gradient of pi. Okay, so this thing simplifies to this thing. Okay, there's an interesting identity. Can everybody get it? Right? So if I plug this in here, the second term will disappear. Because it's a curl of a gradient. Okay, so I can show that this thing, okay, gives me that thing when plugged into that thing gives me that thing, and then that thing finally just becomes because this term will disappear. Okay, when it's plugged in there, it will just give me minus Laplacian of R, Laplacian of pi. Okay, because I can exchange the order of these two things now and put the R outside because this term disappears. And then minus, did I have it right? No. That, and then minus tau of R pi, is this equal to 0? This should be the question I should ask myself. This term becomes that term, and then if I look at this thing further, I can write this as curl of R, Laplacian of pi, it should be a k squared here, sorry. K squared pi is equal to 0. Right? This thing reduces to that thing. Now if I impose the fact that this has to be 0, my divide potential satisfies this equation. If I enforce this condition, then my divide potential satisfies this equation. It means that this has to be 0. It means that this has to be 0, and you can go backward. And that this has to be 0 finally. Okay. So if I impose this condition, then curl of h Tm minus k squared h Tm must be equal to 0. Curl of ETE minus k squared ETE must be equal to 0. Okay? So I have to solve this equation, find all the possibilities, plug them in there, get the vector fields using these two identities. Those vector fields must satisfy these two equations. Are there any questions so far? Yes, Ai?
First, you define that equation with the curl of a vector field, right? So you should only be able to define that vector field up to the gradient of something.
Right. I do it backward though.
Okay.
I cannot define this uniquely. Of course, curl of something is never unique because you can add a gradient to it. It's never unique. But if I impose this condition, I guarantee this condition. If this is true, that is true. Okay, I cannot do the reverse.
What condition will enforce
This one. I demand that my pi, my divide potential satisfies this equation.
Oh.
Then I can go backward, right? It's like a sufficient versus a necessary condition. This implies that, but that doesn't imply this. Okay? This implies that. Okay, I think this is called sufficient condition. This is a sufficient condition for this to be true. But this is not the sufficient condition for this to be true. Okay, so this implies that does not imply that.
It's physically the 0 can be replaced with some other constant. That means a unit before.
Source.
Right, you can have some uniform source and something that constant. I think that will make it to 0 too. This could be a constant. This equation.
So by imposing this, we're not throwing away some solution.
What is that?
By imposing this condition, we're not throwing away some solution.
No, not
to
throwing away
pi.
some solution because I am saying that all the pi's that I have obtained from here is complete. Okay, I can have other solutions, maybe more complicated. Maybe some strange source of R. If I work out all possibilities, this might be the most general solution. I'm saying that because the set of solutions that I have obtained from here, if I treat this as an eigenvalue problem, and this as eigenvector, okay, they're complete that all solutions of this equation can be expanded in terms of the eigenfunctions of this equation because of completeness. This belongs to the class of problem called a Sturm-Liouville problem. Okay, the eigensolutions, eigenmode solutions, they always give you a complete set. So you don't have to go and solve this problem, which is more complicated. Okay, you did not throw out any important solutions by doing this also. Okay, that's a good question. Any other questions?
I have a question. Like the form there, like is a pre-assumption or is a theorem? I mean the field, like is as a curl, like R pi.
These are assumed by divide, right? You must be the first one to have
That's
done it.
assumption, right?
Is what?
It's assumption or like it's a theorem.
What is assumption? And he has to prove that this assumption is true and is correct. He must have been motivated by the fact that if this sphere is infinitely large, if this is the Earth's surface, radius of curvature is very large, then it becomes a layered medium. And in the case of a layered medium where the radius of curvature is very large, we can decompose waves into TE and TM. So one good try will be to try this out to see if I can decompose the field inside the layered medium into TE to R and the TM to R type. Why don't I try this? If I try this, the solution must be curl of something like this. And curl of something like this becomes TE to R and TM to R. And then the further thing I should try next is to see what the conditions I have to impose on my pi in order for this to be a solution to the vector wave equation. Okay, it's a very bold assumption, it's a very clever assumption. It seems that if you put R hat here, say if you put a unit vector here, it doesn't work. You can try, go home and try. Okay, it doesn't work. Okay, this would give you TE to R. This is a unit vector, it doesn't work. It has to be like that, then it works. Okay, very clever trick. And this trick of piloting vector is not only used here, it's also used in solving waveguide problems that you might have encountered, but there it's easier to prove and see. Okay, say if I have a waveguide problem, maybe a more general waveguide of arbitrary shape. Okay, and this is my z-axis. And it turns out that the field inside a TEC waveguide, a perfectly electric conducting waveguide, the field inside can be decomposed into TE to Z and TM to Z. Okay, in order to construct this kind of wave, you assume that E, TE is curl of Z psi. Okay, psi H maybe, I call it psi H. H, TM. Okay, this will be clearly TE to Z because there will be no Z component, curl of Z psi E. Okay, Z is the pilot vector here. You can go through the argument that if these are solutions to the Helmholtz wave equation, that E and H will be a solution to the vector wave equation. You can go through the same argument. Like what they did here, but algebra is a lot simpler because this is a Z hat. It's a Cartesian coordinate system. There's a spherical coordinate system. The algebra is more complicated. Okay? And this is what you do in waveguides, generating TE and TM using this piloting vector. Okay? And you can do the same thing for the layered medium too. If you want to be fancy, you have a layered medium, and then have a piloting vector there, and then generating TE to TM wave in the layered medium using this kind of scalar potential approach. And then instead of solving the EZ and HZ, you can look for the equation for the scalar potential and reduce that to a scalar problem too. Okay, so many problems can be solved by this piloting vector trick. But this is the most difficult one. So if H is that and E is that, then we can write down the total field. Okay, the total field will be sum of these two. So in general, H will be H TM plus H from the TE field as well. But we know that HTE must be curl of ETE divided by I omega mu. Okay, this is Maxwell's equations. This is a source-free Maxwell's equations. Yes?
I have a doubt in the identity which you derived.
Which one?
This one.
The last one?
Yeah.
Okay.
So there, what we did was we considered Cartesian coordinate and improved this identity, right? Can we derive the same thing using spherical coordinate?
No. If this is R hat, you cannot take R hat out. Laplacian of R hat is not equal to R hat Laplacian. It doesn't commute. Why?
So the only way to derive this is through Cartesian.
X, Y, Z are constants. No matter where you go in space, X hat is always pointing in the same direction. But in a spherical coordinate system, R hat points in this direction over here, but in another place, R hat points in a different direction. So the R hat is not a constant vector. Because it's not a constant vector, it must be a function of X, Y, Z. It depends on where you are in space. So you cannot pull it outside. It does not commute. But this X hat, Y hat, and Z hat are always constant. They always point in that direction no matter where you go in space, right? Walk around the world, it still points there, right? Like a compass. Yes? Yes? You have a question?
Yes, because the pi is a vector, right?
Pi is a scalar. Scalar.
Okay, scalar.
Yeah, scalar. In my course, I always use a bar. I use a bar to denote the vector, and a double bar to denote the diode, and nothing to denote the scalar. Okay, this is not true for mathematicians. So use the same for everything. You read math books, vectors, matrices, diodes, everything is denoted by something like this. Okay, so you have to figure it out in the context of the discussion.
Because I think for the Leibniz and this line, there should be another term minus R curl Laplacian pi minus R multiplying k squared curl pi.
So let's see, did I miss out any term? I started out with the vector wave equation. I started out with this, saying that this is equal to that. That is equal to that. So I plugged it in. I get that. This is, I didn't throw any terms, right? And then the remaining term will be that. I start out with this, and this goes here, right? Equals that, and then this is the additional term I add in, and then I convince you that this thing can be simplified into this. And then the gradient term can be thrown out. And then I have this.
I think this line is true, but for this line to the second line, there should be another condition also imposed, right? Because from chain rule, there are another line other than the second line.
No, the condition is that k squared is a constant. K squared is a constant, so k squared can be put in front of the pi. Okay? And then curl of R is just a factorization, right? I just factorize curl of R. But this curl, be careful, this curl operates on everything to its right. This curl operates on everything to its right, not just curl of R. This operates on everything. That's what the curl operates on.
Because I think one for chain rule, there should be something like.
No, right? No, there's no chain rule, it's just a factorization.
Okay.
Say if I have a matrix A times a vector x, and then here I have another vector say a vector A times a vector P times a vector X, matrix A times a matrix B times a vector X, and over here I have K squared. Think of this as operators. Okay, A times X is equal to 0. I can definitely write this as the operator times P minus P dot X minus K squared X is equal to 0. Right? I'm just going from here to here. This is the same thing. Think of these operators as the same as matrix operators. I'm going from here to here. This is the same as going from here to here. I just take the operator outside. And this operator now acts on both terms. Okay? So I didn't leave out anything. Any other questions? Okay, if you're comfortable with this, we can move on. Okay, so here is what I have for the total field, which is curl of R high E plus 1 over I omega mu curl of R high M. Okay, I think I call it pi M. Oh, well, let me call it pi M then. Okay. So the total field is just the sum of TE and TM fields. And similarly, the total E field is also the sum of TM and TE field, and it can be written as curl of R phi E. Okay? That's the total field. In a spherical layered medium, in the place where it's homogeneous. If it's homogeneous, then this is true. If the medium is homogeneous and isotropic. Okay? And then comes the hard part. So this part takes quite a bit of algebraic manipulation in vector algebra. So this is a very important identity that I wouldn't want to erase. Let me keep this identity around. This will be necessary for the next derivation. Okay, you're convinced that this is true. Let me see. Then I want to extract the R component of this field. And that would be the difficult part, actually. And if I were to want to extract the R component like HR and ER from this equation, it's quite clear that the first term provides no contribution to R. Okay, I want to extract HR and ER in a very similar spirit that I use EZ and HZ in the layered medium to characterize TE and TM waves. So I want to use ER to characterize TM wave. I would like to use this to characterize TE wave, very much like we did in layered medium. EZ is TM to Z, HZ, TE to Z. Okay, these are for TM to R, TE to R. Yes?
Aren't pi E and pi M like analogus to the oscillating potentials that we use, A and F?
A and F. Did we use A and F before? Are you talking about another course you learned?
Coulomb gauge.
Huh?
Yeah.
She's asking the scalar potential of
Yeah.
Coulomb gauge.
Coulomb gauge?
Yeah.
For
The
phi
A and
and
Fs
A.
that we use to derive the TMZ and GZ waves.
Electric vector potential.
Oh, okay.
Yeah.
Oh no, they're not the same as those. That decomposition is only valid for homogeneous medium. I'm going to extend this to layered medium finally. It's not the same as that. It's not the same as that. It's not the same as that. Okay, because in that one you define a vector potential A, and then you can say B is curl of A and something, and then you define another one for, I guess you say B is curl of A, because divergence of B equal to 0, and then you say D might be equal to curl of F, because divergence of D is equal to 0 kind of thing, and then you come up with two vector potentials, and then you try to derive some equations that look something like this, but these are not the same. These are not the same thing. Okay, these are vector potentials in another context, but this is intended for layered medium. Okay, this is for homogeneous medium, but here we want to make one of them Tm. Okay, the other one is contribution from the TE part. This one is Tm. This is Te, and this is a contribution from the next part. So this is more like a decomposition into Te and Tm waves, rather than what you do in maybe ECE570. You do something like that. Okay. The vector potential contribution A, which comes from the magnetic vector potential, F comes from the electric vector potential, and then there's no decomposition into Te or Tm waves there. Okay, it's just a general way to solve a source-free problem. Okay? So we want to do this, and it's quite different. And I like to extract the R component of this field, and that is the tricky part, as I said before. I said it many times, so it must have taken me quite a while to derive this expression. So if I extract the R part of this, then I first have to look into this in greater detail. And again, I use the vector identity I have learned as an undergraduate, that this must be curl of the divergence of R pi, okay, minus the Laplacian of R pi. Okay, this identity comes in useful again. Okay. So if I were to use this identity, this would be equal to the gradient of the divergence of